So, good morning, everyone. My name is Michele De Gennaro, and I'm glad to present here the project that I coordinate. The project is Fitgen. Fitgen stands for Functionally Integrated Axle, ready for mass market third-generation electric vehicles. The project now is finishing the second year of life. In June 2020, we had the midterm review, and the results that I'm going to present here refer to the first 18 months of the project. Fitgen was submitted in February 2018 to respond in full to the challenges of the LCGV1 call. The project objective is to deliver a brand-independent axle with advancement in three main areas: the power electronics and the charge area, the electric motor and transmission area, and the cooling and control. An important aspect of Fitgen is the achievement of technology readiness level and manufacturing readiness level equal to 7, with full vehicle demonstration of the performance of the axle in type approval condition and in freeway driving condition. One important objective, in fact, is to reach a full electric driving range on freeway driving between 700 and 1,000 km a day, including 3 stops for recharging the battery of max 25 minutes each. Last, the production cost target of €2,000 a unit by 2030 is a key element to exploit the market potential of the innovation portfolio proposed by the project, as well as ensuring the adoption of the Fitgen axle on a variety of vehicle brands and configuration. These slides present the overall concept of the project and the electric architecture of the axle. At its very core, we have the motor, which is a 6-phase 800-volt permanent magnet machine coupled with a single-speed high-efficient transmission. Upstream, there is a 6-phase 800-volt inverter, which makes use of the latest silicon carbide technology connected to a bidirectional DC-DC converter. This has the dual use in traction mode to step up the battery voltage from 400 to 800 volt, and in charging mode to step down the charging voltage from 800 to 400 volt, reaching 100 kilowatt, 120 kilowatt peak of power for charging, 80 kilowatt continuous charge, enabling super fast charge. The electric architecture is also equipped with a commercial AC/DC charger at 11 kilowatt. The WLTP type approval DISA-specific energy consumption target for the project is expected to be 120 watt-hour a kilometer and around 140 watt-hour a kilometer for freeway driving. These slides reports and focus looks at the results of the e-motor and transmission. The e-motor is developed by Brusa and the transmission is developed by GKN. The development challenge for Fitgen was to reach the optimum balance between the requirements of high efficiency, high volumetric and gravimetric power density, and low cost. To do this, the motor technology adopted is a permanent magnet hybrid synchronous motor in 6 phases. The rotor has 3 layers of flux barriers and high remanence magnets, while the stator adopts state-of-the-art formless wire windings patented by Brusa. Performance-wise, at the test bench, the e-motor achieves 5.2 kilowatt a kilogram and 96.8% measured peak efficiency. These values are at the top of the category for commercial automotive products. The motor transmission is designed for, the motor and transmission are designed for maximum speed of 23,000 RPM with a sustained overspeed of 27,600 RPM. This is also top-notch performance. The drive is capable of 170 Nm of peak torque and under 35 kilowatt of sustained peak power. This slide focuses on the development of the inverter. As stated before, this is a 6-phase 800-volt inverter configured in a 2x3-phase cascade setup using silicon carbide MOSFET technology. The inverter design is led by Brusa, while the silicon carbide MOSFET technology is led by STMicro. The electrical design activities for the inverter have been geared towards optimizing the inverter with respect to switching performance, efficiency, and scalability. The result is a very compact design, as you can see from the exploded view on the right-hand side of the slide. The volume of the inverter box is slightly above 5 liters, with a power density of above 26 kilowatt a liter. The inverter and the motor share a common housing, so also a common cooling circuit. as well as no cabling is required between the motor and inverter, and this is an extra advantage of the Fitgen design. Beyond the superfast charging at 120 volts, one of the objectives of the project was also to investigate the possibility of implementing the onboard charger AC into the e-axle, not to have additional hardware required for charging. Here, this activity is under the responsibility of Polytechnic of Torino that has investigated several possible topologies for using the traction motor as a reactive element and the power electronics as an energy converter. One of these topologies is depicted here on the slide. Here we see that the motor is used as an isolation transformer, while one of the three-phase inverter units regulates the charging process. Together with this hardware setup, the Polito has also developed a number of dedicated control strategies to achieve optimal grid current control, minimal harmonic distortion, and avoiding torque production during the charging process. The solution, the best solution, is at the moment under evaluation for a patent. Concerning the cooling circuit, the integrated cooling circuit for the motor inverter, these slides report some of the latest results achieved by the Austrian Institute of Technology. The main objective here is to design and optimize the channels and the labyrinth of the cooling circuit to manage maximum winding and magnet temperatures while satisfying pre-imposed constraints. It was necessary to design a configuration capable of an even flow distribution and capable of minimizing hotspots. A CFD model of the cooling circuit was built up, and CFD simulation were used to select between among different various design candidates and to tune the selected design to a pressure drop of 17 kilopascal. The candidate was then coupled with an heat transfer model to conduct a sensitivity study and optimization study on key geometrical parameters. For example, a mandatory gap between the coolant guiding ribs and the outer housing allows for a leakage flow between the channels. And here, an optimum for the gap size with respect to the winding temperature was found, and the sensitivity of the pressure drop to the gap size was assessed. This slides reports the integration work that has been done so far, virtual, of the Fitgen axle within the frame of the vehicle demonstration platform, which is a Fiat 500 electric. In picture 1, you can see the group of the inverter motor transmission, while in picture 2, you see this group coupled with the CDC converter on top, while in picture 3, you see the integration of all these components in the vehicle frame in rear-wheel driving configuration. To enable this integration, the rear suspension of the Fiat 500D was modified, and this kind of implementation in rear-wheel driving configuration allows for a double advantage. One is to lower the center of gravity of the vehicle compared to the donor vehicle, and the second one is basically freeing the space under the front bonnet, allowing for a second storage volume. At the moment, Fitgen is at month 23 of its total duration of 36 months, and the majority of the components are in the phase of finalization of detailed design. Some of them are already in prototyping, like the active parts of the motors, the inverters, PCBs, and the transmission, while the control software is going to be released by the end of the year. All the components will be ready for being assembled into the final e-axle by January-February 2021, and in Q1 and Q2 2021, the consortium will focus on implementing the control algorithm and testing and qualify at the bench the full e-axle. In Q3 and Q4 2021, the consortium will proceed by integrating the e-axle into the demonstrator vehicle, and will test this on the vehicle in both type approval condition and in freeway driving condition. The final results will also see the complement of an ex-post TRL and MRL assessment, as well as a full life cycle analysis and life cycle cost analysis. We believe that Fitgen, at the end of the project, so at the end of the next year, 2021, will provide solution that will be almost 2 to 3 years away from the market introduction. And here we have to thank the EU funding for accelerating the development of such components. The components of Fitgen will be viable to be implemented in different vehicle segments, also on large passenger car, with implementation in four-wheel driving with one axle on the front axle and one e-axle on the rear axle. Future research can be done in the field of further reducing the cost by reducing the amounts of rare earths in the magnets, just as an example, and optimize overall cost and performance for different applications. If you are interested in learning more about the project, you can visit our website, www.fitgenproject.eu, where you also can find all the latest news on the project and all the downloadable material, public deliverables, and scientific papers. You can register to our newsletter, and you can follow us on our social media channel. We actively use Twitter, Facebook, and LinkedIn, but we're also starting up an Instagram profile and a YouTube channel, where in the next months you will find all the graphical materials and the videos that will be produced by the project. This is my last slide, so I thank you for your attention. And again, in case you are big interest for this project, you can also contact me directly at my email address that you see on the screen. Thank you, and see you at the live session.